big theorem in parametric curves in vector geometry. Um, what is this saying? Acceleration is always a linear combination of the tangent and normal vectors. Okay, so what are we talking about here? Well, given, let's make this a little more formulaic and a little less wordy. Um, so given a parametric curve, right, with formula r of t, r double prime, this is what I mean by acceleration, right? Second derivative. So it's the derivative of, right? The first derivative, r prime, is velocity. Second derivative is acceleration. So acceleration, right? This is always a linear combination. Now this is a word you've certainly seen if you had a linear algebra class. If you haven't, this might be a new term to you. But what linear combination means is it means that there's some scalar times a vector, which in this case is the tangent vector, plus some scalar times another vector. And then, maybe you keep going with more vectors if you're doing a linear combination of more vectors, but here we have a linear combination of just two vectors. Right. So this is what is meant by this. And in again, if you are recalling something from a linear algebra class, this is where you always write things like this, like C1v1 plus C2v2, and maybe it keeps going if there are more. But right, that's a linear combination in general. Here, vector one would be the tangent vector. Vector two would be the normal vector. Um, what are the scalars in this case? Well, there are some functions that we call the tangent component of acceleration and the normal component of acceleration because they're the scalar quantities in this equation, right? So this is called once again the tangential component of acceleration, and this is called the normal component. So it's saying that of acceleration. It's saying that at any moment, you can always break down acceleration into a combination of tangential acceleration and normal acceleration. Um, from a sort of a physicsy mindset, this is a nice concept because it's saying that there are two ways a moving object can accelerate. This is saying it can go faster or slower in the direction that it's already headed, right? The tangent vector shows you what direction you're currently traveling. So that's one way you can accelerate is, an extreme example of that would be you're just moving along a line, but you're moving faster and faster along that same line. That's an example of acceleration. That would be all tangential acceleration and no normal acceleration whatsoever, right? The extreme opposite would be is the normal component of acceleration. That means you can accelerate because you're turning, right? That's what's causing your direction to change, right? That's another way that you can accelerate. Okay, so these are the two types of acceleration, right? Acceleration is always composed of these two. Um, let's do a proof. This proof I think is super nice. You get to use lots of lovely vector properties, and it's going to give us, best of all, this proof is going to give us formulas for AT and AN. So it doesn't just show that they exist, but it's going to actually calculate them for us. So here's the really lame trick that this um, here that this proof starts off with. R double prime. What's R double prime? It's R prime pos prime, right? So this is the first step of this proof. Why might I do such a thing? Well, I'm just starting on the left-hand side, and I'm just trying to get to the right-hand side. Why is this progress? Well, because what's the definition of t? Definition of t is r prime over magnitude of r prime. So that's why I wanted to rewrite it as a single prime, right? But I can't just randomly divide by speed like that unless I also multiply by speed, right? Now I've um, kept my expression equal to the previous, right? By multiplying and dividing by the same quantity, right? Notice here, we are implicitly assuming it's smooth, right? because I'm assuming the tangent vector is defined, right? I'm assuming speed is not 0. I just divided by speed. So, okay. Assuming it's smooth is not a big assumption, right? It's like if you have a theorem about derivatives, so you're assuming your function is differentiable. Otherwise, you can't state the theorem. Same thing here. So, all right. So what do we have now? I have tangent vector times speed, right? Use a product rule, right? So use a product rule. So take a derivative, leave it alone. Take a derivative, leave it alone. What does this become? Well, this is done, right? This is what we wanted. Well, there's the tangential component, right? So that component's fine. This component is almost done. I need the normal vector there, which isn't quite tangent prime, but it's not far away. All I have to do, right? What is the normal vector? It's just tangent prime divided by the magnitude of tangent prime. Beautiful. So just also multiply by the magnitude of tangent prime, and now you've kept the expression balanced. Okay, now we have it. Right, there's the normal vector, right? T prime over magnitude T prime. There it is. Great. So what is this? This is the tangential component of acceleration, right? And this is the normal component of acceleration. So we did it, right? We proved the theorem is true, right? Right, the theorem is true. And the formulas, right? As a bonus for AN, AT, and AN are shown above. There we go. Almost. So there is our, that's our theorem, right? So this theorem that acceleration always decomposes into exactly these two quantities is true. It's just great, right? It's the product rule that does it for us, right? That's how you get a derivative, and the acceleration is a type of derivative. How you take that derivative and split it into a sum of two terms. Well, product rule is good at that, right? Kicks out extra terms. So there we go. So there's our little theorem. Let's then look at this in an example. So let's verify this theorem in a specific example, right? Let's check that this actually all works out, not just, in general by doing symbolic calculations of vectors, but in the case of this parametric curve. Which, if you saw my previous video on this playlist, we already calculated a bunch of quantities about this, right? This is a parameterization of an inverse parabola, right? And here, what do I mean by verify? I mean, let's compute the left-hand side and the right-hand side, and hopefully they match, right? So let's compute them independently, right? So the acceleration, that's the easy part to calculate, right? The velocity, the right-hand side is an epic endurance log, right? The left-hand side is quick, right? So this is 2t, one is the velocity, and then acceleration is just 2 comma 0, right? So there's the acceleration. That's the left-hand side of the theorem, right? Is the acceleration. Now so halfway there, sort of, in a weird metric. Not the effort metric. We're not happy with. So, all right. So then we need the right hand side, right? So now let's calculate. Let's calculate a t plus a n, right? Which is the right hand side. So let's calculate this and verify that it actually gives us acceleration. Right? Let's verify that it does actually equal r double prime, which is just 2, 0, right? And for this curve. Okay, so let's do that. So I'm gonna pull from the previous video, right? If you want to see the details on that, go reference that video. But I'm gonna pull a lot of the relevant quantities here. Lots of these we already calculated. So in particular, we already had the tangent vector calculated. We already had the normal vector calculated, right? And they are conveniently up here on the same notability sheet. So by no accident, right? So there's our normal vector from the previous video. Right, once again, if you want to see the details of how we got that, just check out that previous video. We need the tangent vector, right? Tangent vector was this. Right, so let's get the tangent vector as well. Right, so there's tangent and normal. So those are these vectors, right? We have those. Then I also need AT and AN, and those formulas I just found up here, right? So what is AT? So A sub T is, like I said, it's speed prime. And what was speed? Speed was square root of 4t squared plus 1. You can kind of see it right there, right? That's what we divided by when we were doing our tangent vector. So that's this derivative. So I get, I do power rule, right? So there's speed, speed prime, right? So that's our linear component of acceleration, right? Sometimes if you're in physics, sometimes it's called v prime, right? The way that gets written sometimes. All right, then we have AN, right? And what is our AN? AN is up here, is where we have our formula for AN. It's speed times t magnitude of t prime, right? So it's speed times basically it's speed times angular speed, right? Is what we're looking at here. So speed was this quantity, right? And then what was angular speed? This was also calculated in the previous video, right? So there's our angular speed. Okay, so then A sub n is that, right? 2 over that square root. All right, so now let's put it all together and let's see if it works out like it should, right? So let's calculate this now, right? So I have all the pieces there. So the final calculation, I'm going to have A t times t plus a n times n So let's see what this is. So 4t over root 4t squared plus 1 times a tangent vector. Right, then I have a sub n, right, the normal component, times n, normal vector. Okay, simplify. The product of the square roots, simplify. The product of the square roots, right? Factor out now I'm going to factor out what these have in common, right? So big common factor here is 2 times, or sorry, 2 over 4t squared plus 1, right? What does that leave us with? Here it leaves us with 2t, that scalar, and then the second expression, that was the whole scalar. It was just that 2 over 4t squared plus 1, right? Okay, so what do I have now? Multiply your scalar through, add the vectors, and celebrate because these cancel, so it leaves us with 1, right? So it's 2 times 1 is 2, and there's 0. Anything times 0 is 0. There's acceleration. It worked, right? So there we got to witness the acceleration vector being decomposed as claimed, right? Into the into what? Speed. So speed prime times a tangent vector plus speed times angular speed times the normal vector, right? There's our decomposition of acceleration. So it worked. Great. Thanks. More fun with vector geometry to be had soon.